I want to talk today about stoichiometry. It's a scary word that students of chemistry really need to understand. There's a lot of questions that form stoichiometry, and it is the basis for pretty much every experiment that you do. Now, here's the thing. Chemists work in things that can be measured. Chemists work in things that can be measured. What do I mean things that can be measured? Well, we work in grams. For example, I might start with 10 grams of silicon dioxide, and if I want to liberate the oxygen from that, I might be able to work out how many grams of oxygen I can liberate from some silicon dioxide. Or I might be dealing with 3 liters of hydrochloric acid. What concentration of hydrochloric acid? At 6 molar concentration of hydrochloric acid. Or I might be dealing with a volume of gas, let's say 14.6 litres of ethane gas. So if we're dealing with measurable quantities all the time, why do we need to deal with moles? You see, moles are not measurable. And what I mean by that is we don't have any scale or machine to measure moles. We have scales that measure weight. You can use a measuring cylinder to measure volume. You can work out the concentration of something by measuring the pH. But moles are not measurable. Moles are calculated. So what do I mean by moles are calculated? Well, we have different equations. So if I'm talking about mass, I use this famous equation you can use all the time. Moles equals mass over molar mass. Let's say I'm talking about concentration. So my concentration is, concentration equals moles over volume. Or if I'm dealing with just volume by itself, so if a volume of a gas, that equals the number of moles divided by the number of litres of gas at whatever atmospheric conditions. I think at 25, it's about 24.5 litres. So when I say moles are calculated, we often have to calculate moles. So if we don't know the moles, but we do know the other values, then we can plug the other values into our equations and boom, out pops the moles. Plug these values in, boom, out pops the moles. Sometimes we do know the moles, but we don't know the mass, and since we always know molar mass, we can look at that up on the periodic table. We then can go back to moles, but usually you're dealing with not knowing the moles, and then knowing the mass, and knowing the molar mass. So still, why work in moles at all? Why don't we skip that? Well, we don't have a way of going from grams of one substance straight to grams of another substance. Let me show you why. There's a reaction that happens, it takes in energy, it's an endothermic, not an exothermic reaction that happens in the roots of plants. What it is, nitrogen from the air, let's work in black because I like that better, nitrogen from the air mixes with hydrogen, which they actually get from water, they break down water, and it gives off ammonia gas. Some bacteria do this. Now, unfortunately for chemists, I can't deal with measurable quantities. I can't say 2 grams reacts with 2 grams to give 4 grams. I mean, you will get that, but from the chemical equations don't deal with grams. They deal with numbers of atoms reacting together in fixed ratios. Let me explain. So to balance this equation, I can talk about one molecule, just one molecule of nitrogen reacting with 3 molecules of hydrogen to give 2 molecules of ammonia. I can scale that way up to moles and say that I have one entire mole, one lot of 6.02 times 10 to the 23 lots of atoms reacting with 3 entire moles to give 2 entire moles of ammonium gas. When we deal with moles, we're talking about mole ratios. 1 is to 3 is to 2. So let's say I don't have an entire mole. I only have half a mole. Well, if I only have half a mole of nitrogen, then I only need 1.5 moles of hydrogen, and I only need 1 mole of ammonia. I can do the other way around. I can say 2 is to 6 is to 4. Or I can even do decimal places. Let's say if I have 0.63, I'm going to need 3 times that, 1.89, and I'm going to need twice that, 1.26. You can see these are fixed ratios. These ratios here, this ratio, this ratio, this ratio, this ratio, are all the same. In your textbook, you might see a question like this. How many moles of N2 do I need in excess H2? So I'm not going to worry about the H2. I have excess, I have as much as I need to produce 3.7 moles of NH3. In reality, this forms part of what chemists will do, but you're never really going to start off with knowing how many moles you need to produce. Usually the question would actually ask how many grams, because that's something that's measurable, or maybe liters. But it's useful for part of the equation, and we'll start here. So how would I go about doing that? Well, here's my ratio between nitrogen and ammonia. My ratio is 1 is to 2. Let's write that down. 1 is to 2. Now, since ratios are always equal to each other, 1 is to 2 is equal to 2 is to 4. And that is equal to half is to 1. That's all the same ratio. So again, our ratio is 1 is to 2, which is the same as 2 is to 4, which is the same as 1/2 is to 1. So I'm dealing with my molar ratio. I start off with 1 is to 2. Remember, this 1 here refers to the nitrogen, the 2 here refers to the ammonia. Now, what's my ratio on the other side? Here's how I do my mole ratio calculations. So I know, I'm asking how many moles of N2 do I need? I don't know that, so I'll leave that as X. How many to produce 3.7 moles of NH3? Well, I know I'm trying to produce 3.7. So there, I've got my ratio. 1 is to 2 is the same as X is to 3.7. So what is X? Well, I have to use some algebra here. Now, this is something you might not know, but ratios can also be represented as fractions. So 1 over 2, or 1 divided by 2, is the same as x divided by 3.7. Get to the next step, I simply cross-multiply. You can use other algebra methods, but I find cross-multiplying is the best. So that gives me 3.7, or 1 times 3.7, equals 2x. And I'll do the rest of the equation over here because I'm running out of space. So there's my 3.7 there. Just make sure that you can see that's a proper 7. So if I divide both sides by 2, 3.7 divided by 2, that gets x by itself. So I'm ending up with 1.85 equals x. So in summary, how many moles of N2 do I need? I need 1.85 moles. Let's write that in. Fantastic. What we did before is called the mole-to-mole conversion. That's your staple of stoichiometry. And you always need to do a mole-to-mole conversion. Sometimes it's called a mole ratio because we looked at the ratios of one mole to another one. This is your staple. The number one thing you need to do in stoichiometry. But as I said before, often we're not given the moles. You're actually given something, let's say, in grams. Or it could be volume, or it could be concentration. But let's use grams for now. And what this equation is would be a mass. If we're using grams, it would be a mass. If it was volume, it would be using volume. But this case, it's mass. So mass to mole equation. Now, a mass to mole equation is a mole to mole equation, or a mole ratio, but with an extra step at the front, so we can actually convert our mass to moles. Let me explain. So our question could be, I have 3.3 grams of H2. How many moles of NH3 will I make? Now this is becoming more like something we would really see, because we're starting with a measurable quantity. We've measured out 3.3 grams of H2. Remember, you could also do it in volume, and then you'd need to use the volume equation with moles that I told you before, but this time we're going to use mass. And how do we go about this? Well, my equation, let's write it out again. I'll do it just up to the left-hand side. So again, I've got nitrogen reacting with hydrogen to give ammonia. Always need to balance that out. So that would be 2, 3, and 1. I'm not dealing with grams. I can't say this does not mean 1 gram reacts with 3 grams to give 2 grams. How can 1 gram plus 3 grams give 2 grams? That breaks the law of conservation of matter. That would be 4 grams would have to give 4 grams. No, it's because it's in molecules or moles. 1 molecule gives plus 3 molecules gives 2 molecules, or 1 mole plus 3 moles gives 2 moles. First, what I need to do is to convert 3.3 grams of hydrogen into moles. I have to use my mole equation to do that. So step 1 is to do a mass to mole conversion. Mass to mole conversion. So here's my equation for that. Now m in this case equals 3.3, my little m. My big M, my molar mass, well, the molar mass of H2, H is made up of H2 is made up of 2 atoms of hydrogen. Each atom of hydrogen has a molar mass of 1, so 1 plus 1 equals 2. So now I've got that, and I'll just circle that so you know it's all related. Let's finally fill it in over to the right. So n, still don't know what n is, equals 3.3 divided by 2. The answer is, this equals 1.65 moles. And I've run out of space there to write it, but you can see that that is moles. So what is step 2? Well, step 2 is exactly what we did before, the mole-to-mole conversion, sometimes called the mole ratio. Now we know the amount of moles that we have, we can then work out how many moles of NH3 that we need. So now we know the number of moles of hydrogen. We've converted 3.3 grams to moles. We can do our simple ratio. So again, my ratio of H2 to NH3 is 3 is to 2. Let's write that down. 3 is to 2. So it's going to equal 1.65 is to x. We're not sure what our new value is going to be for the NH3. Let's express that now as a fraction. 3 over 2 equals 1.65 over x. Cross multiply it out. 3x equals 2 times 1.65. 3.3. And I'm running out of space, so I'm going to do the rest of it over here. So x equals 3.3 divided by 3, which is 1.1. Let's just double check that. 3 is to 2, 1.65 is to 1.1. That sounds about right. Let's write in our answer. I will make 1.1 moles of NH3. So we've fully completed the answer to this question. But in reality, leaving it as 1.1 moles of NH3 doesn't tell us much. We want to convert this 1.1 moles of NH3 back to some sort of measurable quantity. Let's say grams again. Let's get rid of all the writing and move our answer up here. So I have 3.3 grams of H2. How many moles of NH3 will I make? I'll make 1.1 moles of NH3. Again, 1.1 moles doesn't tell us a lot. What we've done is we've just done a mass to mole. In the mass to mole, we actually had to do a mole to mole in between. Because once we got the moles from the mass, we then had to convert the moles of H2 to the moles of NH3. In reality, we probably want to know something like the grams of NH3. So we'll need to do a mass to mass equation. What is a mass to mass equation? It just involves one extra step. We take this here, the 1.1 moles, and then we use our equation, N equals little m over big M, the mass to mole equation, to simply convert that 1.1 moles back to mass. So let's delete all our writing there, and let's start. So N equals little m over big M. N, actually this time we know what it is. It's 1.1 moles. Our little m, that's what we don't know. Our big M, what is the molar mass of NH3? Well, it's 14 for nitrogen plus 3 lots of hydrogen. So that gives us 17 grams per mole. Grams per mole means 17 grams in every mole. Okay, let's plug the values in. 1.1 equals, I'm going to keep that as little m since it's a question mark, divided by 17. 1.1 multiplied by 17 will give us m by itself. M by itself is 18.7 grams. So now you've done the hardest stoichiometry equation. You've done the dreaded mass to mass. It's not that difficult. Now, I will just say one final thing. Let's say we didn't have this in grams, but we had this in 3.3 liters. And then my question wasn't, I'll make 1.1 moles. My question was wanting not how many grams of NH3, which is what we just done now, but how many liters of NH3. Well then, instead of using this equation here, we would use the liters equation that I gave before. Volume equals moles divided by whatever the volume of gas is at your conditions, say 24.5, this is at 25 degrees Celsius. So that would be my equation there. Very simple, just a very small change. And I know you did that in your assignment, but it's important to conceptualize what you're doing. So you're saying, now I've got this in grams, I need to go to moles. If I want to go back to grams again, from one reactant to one product, I need to always go through. So the lesson today is all roads, not lead to, go through moles. And here's my drawing of a mole for you. It's a hairy-nosed mole. It's got hair on its back, little ears, oh my goodness, and a tail. And he's carrying a sword.